This video discusses the problem 3 of midterm exam 2 solutions. Okay, so this problem is on a PFC, power factor correction circuit, shown here. The input voltage and the current drawn from the grid IS, those are given, and we need to calculate the output voltage and draw various waveforms. Okay, so we'll start with part A, which is to calculate the output voltage, which is actually fairly simple because we are going to use power balance to calculate the output voltage, because once the input voltage and input current are given, it's easy to calculate the power drawn from the grid, and using power balance, there is the power at the output as well, and knowing the output resistance is 60 ohms, we can calculate the output voltage. So Pin on the AC side is the Vs peak or Vs hat times Is peak divided by 2. That is the input power, or Vrms times Irms, either way is fine. So Vs peak from the given Vs is 340, and the Is peak is also given, which is 20 over 2. Okay, that's 3400 watts. Okay. So P out is also therefore 3400, and P is V square over R, therefore VO would be square root of P times R, PO, which is 3400, times the resistance is 60 ohms. So that gives us the output voltage to be 451.7 volts. Okay, that is the answer for part A. And as a check, you can verify that this being a boost based PFC, the output voltage has to be at least greater than the peak of the input voltage, which is 340, and we are well above that at 451. Okay, the second question was to calculate the duty ratio, DFT. Again, for a boost converter, we know that DFT is 1 minus the input voltage divided by the output voltage. So in this case, it is 1 minus 340. So it's a DC, so we want the absolute value, sine 2 pi 50t. That is the input voltage divided by V out, which is a constant which we just derived in the last slide, 451.7, gives us the answer to be 1 minus 0.753, the absolute value of the sine 2 pi 50t. Okay, that is the answer for the duty ratio. Okay, then we are asked to, as part C, we are asked to write the expressions for all of these cycle by cycle averaged quantities, CCA. So CCA always refers to averaging at one switching period. So that is a basic definition. So I saw some students try to take the average of the rectified sine or sine, which is not correct. CCA always refers to switching period, average over one complete switching period. Okay, so that makes the solution to this part C is really simple, especially the first two. Okay. Vrect is the waveform just after the diode bridge. It is just nothing but the rectified source voltage. Right? So if Vs is 340 sine omega t, then Vrect is nothing but absolute value of that. Right? So it's as simple as that. So Vrect average as a function of t is simply 340 peak value, absolute value of sine 2 pi 50. Same thing for IL. IL average, cycle by cycle average over switching period, is again the input current I is rectified. That is how we control the inductor current. Actually, that is the cause. We control the inductor current to have this wave shape, and there the input current therefore becomes this pure AC current. Anyways, IL of t is the absolute value of IS of t, which is nothing but the given 20 amps peak times the same sine 2 pi 50 t. Okay, then IC bar, we have in our notes an expression derived, so which was actually minus P out, the output power, divided by the nominal output voltage VO times, this comes out to be actually cosine, and at twice the line frequency. We derived this using, actually we used power balance to derive this. Okay, so that is minus 7.53, that is the P out over V out value. 53 cosine of alright, that is 2 pi times 100, 2 times 50 t. Okay, so this voltage, this is current, and this is current. Okay, and the last of the CCA expression that we needed was the output voltage, complete output voltage average, cycle by cycle average value. Okay. So if you looked at the notes, there is an expression that we derived for just the viewer ripple CCA. Okay, that was derived in the notes as 1 over C output power over the nominal output voltage 1 over 2 omega, where omega is just 2 pi 50 t. Okay, this is just the viewer ripple, but the output voltage, complete output voltage cycle by cycle average, will definitely include the DC value, right? Plus of course this viewer ripple. Okay. This is VO function of time. Okay. So the final answer for the CCA of the output voltage would be the nominal for 51.7 plus this calculated value comes out to be, actually it's negative 19.33 sine, so VO ripple of TV, this is just the magnitude, amplitude of sine wave, this is sine 2 pi, again at twice the frequency, which is 100 t. Okay. So minus 19.33 sine of 2 pi 100 t. Okay. So that is VO bar as a function of time. So many students got the viewer ripple part correctly, but that is not the only component in the full output voltage. The larger part is of course the DC value, so that just cannot be neglected. Then the main part of the problem is to draw some switching frequency level waveforms. These are the inductor voltage waveform defined here, then the inductor current waveform, and the capacitor current flowing here. And these switching frequency level waveforms are to be drawn in the interval 7 milliseconds to 7.01 millisecond, which actually covers 2 switching periods. Our switching frequency is 200 kilohertz, or TS is 5 microseconds. So this difference here is 0.01 milliseconds or 10 microseconds. So you have 2 switching periods. So in order to draw these waveforms, first we should know what is the value of different parameters at t equals. So we will select 7.005. Okay, and then assume that is the value at during this interval for many of these cycle by cycle average values. So in particular Vrect, so at t equals 7.005 millisecond, the Vrect, if you recall, Vrect was just absolute value of this 340, absolute of sine 2 pi 50 t. So in that, substitute t equals 7.005 10 to the minus 3. That will give us the Vrect at that instant. So that comes out to be 274.75 volts. So this is at 7.005 millisecond. So you need to be careful when you substitute t equals the 7.005 10 to the minus 3. What you get is the angle in radians. So you need to convert that to degrees by multiplying by 180 over pi, and then take the sine of that. Or you set your calculator to directly work with radians. Okay, so then the other one that you would need is IL, again at 7.005. So substitute in this here t to be 7.005 millisecond. You'll get IL to be 16.16 amperes. Again at 7.005 millisecond. Then the duty ratio, which is certainly needed for all the waveforms. Again at that interval, that 7.005 millisecond comes out to be 0.3915. Okay, again recall that we derived explicitly the d of t and substitute t to be this value. Okay, then if you need, you can also dts will be multiplying 0.3915 by 5 microsecond, gives you 1.958 microsecond. Okay. All of these again at this specific time. We can calculate VO also, but I did not really expect the student to calculate VO of t exactly at that instant. You could use VO. Okay, you can just say VO is approximately equal to the nominal value VO, which is 451.7. So the more accurate one would be to calculate VO of t at this duration, this time interval, which will come out to be, I think, something like 470 volts or so. Okay. But either of the two is okay to use. Okay, the first waveform to be drawn is VL of t. Looking at the inductor, it is V rect minus the voltage at this switching node. So this is a constant value in that time interval, whereas this voltage, node voltage, is switching between 0 when the switch is on for a duration of dts, and V out for the duration of 1 minus dts. So we can draw the V rect waveform, VL waveform, which clearly is a switching AC voltage waveform. This is VL. This point is 7 millisecond. This would be 7.005 millisecond, and this would be 7.01 millisecond. Okay, and then let's say this is your dts period. Dts again, positive voltage here, which is V rect, and negative voltage. It's a continuous line. Then positive again. So that will be the VL waveform, and we need to determine these magnitudes. So this is the on interval. The VL is nothing but V rect because the switch is on, therefore this end is 0. So VL is simply V rect, and that is 274.75. And the voltage here, this voltage is V rect 274.75 minus V out, and as I said, we're just going to assume V out is constant, so 451.7. Okay, that was 176 minus 176.95. Okay, and the average of VL came out to be actually a negative number. I believe it's minus 42 or so. So VL average is, okay, I'll write it over here. VL average would be 274.75 times the duration of or D of 0.3915 minus this 176.95, the value for the duration of 1 minus d, it's 1 minus 0.3915. You calculate that. So I think that came out to be negative 40 something. Okay, the next waveform is the inductor current IL, and again we wrote in the previous slide that IL at t of 7.005 millisecond was 16.16 amperes, and we also need the delta IL information. This is boost converter, so you can use the VO d 1 minus dTs equation, or even simpler, we already know the inductor voltage waveform, which we just drew that in the previous slide. So during the on interval, it was the Vrect of 274.75, and the duration was dTs, which also we know, that was 1.958 microsecond times 10 to the minus seconds, Vn dTs over the inductance L, which is this value, 250 microhenry. Okay, so the delta IL works out to be 2.15 amperes. Okay, so with these two we can draw the complete inductor current waveform. It's positive, so just the positive part. So again, this will be 7 milli, 7.005 and 7.1. Okay, so this is the DTS period. So I think I forgot to write this in the previous waveform, but I'll do it here. So this is 7 millisecond plus that 1.958 microsecond, which makes it 1958 millisecond. Okay, so this is nothing but 7 millisecond plus dTs, which is the 1.958 microsecond. Alright, so delta IL is going to be rising during that on interval, then falls back to the original value, then rises again for another dTs, and then comes back to value close to that. It's not a DC-DC converter, so this value is not exactly the starting value. This value is also not exactly its own starting value. It's if it is in the positive half cycle in the before the 90 degrees, is actually increasing. So anyway, we don't have to be that particular. The average value in this two switching cycles is what we calculated as 16.16. Sorry, this is IL bar. IL average is 16.16, and delta IL is 2.15. So this value is going to be 16.16 plus 2.15 over 2, okay, which is 17.235, and the lower value is 16.16 minus the delta IL over 2, which comes out to be 15.085. So that is the complete inductor current waveform. Okay, and the last one is the capacitor current IC, shown as going into the capacitor, and so this is going to be switching between, when the switch is on, there is no current from the diode, so that would be just the entire load current in the negative direction, and when the switch is turned off, it will be this inductor current at that instant on the sine wave minus the load current. Okay, so the I out minus the I out was the V out over the resistance, which is 7.53 amps, okay, which is nothing but V out over the this R of 60 ohms. Okay. So IC, so again positive and negative, this is 7.005, 7.1, and 7.01, and this is t in milliseconds. Okay, so on interval, it's a negative current equal to the load current value. Then it jumps to IL minus I out. Then at the end of the cycle goes back to minus I out again. Then jumps to the peak inductor current minus the load current, so on. So this is minus I out equals minus 7.53 amps, and this value would be whatever was the IL peak that we calculated, 17.235 minus the load current, okay, which I think is 9.71, and this value is again IL minus I out, comes out to be 7.56. Okay. And you can calculate the IC average, cycle by cycle average, during this two switching periods. Okay, so for that I just calculated the average of just the off interval. This current was basically the average of 9.71 and 7.56, which I calculated was 8.63. Okay. Then I wrote IC bar as this minus 7.53 for a duration of D, okay, plus the 8.63 for a duration of 1 minus D, and I got the IC bar to be 2.3 amps. Okay. So once again you can see that IC bar is not 0 as you would expect in DC-DC converters, but here this is AC steady state, where IC bar is not necessarily 0. It would be on a larger time scale. It would be fundamental frequency or twice the fundamental frequency current will have a non-zero, fairly low magnitude. Okay, so I think that completes problem 3. So that is the